All right, so I'll just start us off. We are Team CySLI, and this is our fall readiness review. So this is an overview of all the team members and the team structure that we've laid out. You can see there's 4 sub-teams: the rocket team, payload, AGSE, and avionics. Of course, team lead is myself, and then there's Rebecca there, which is the outreach chair, and then Connor Duffy is the safety officer. Project overview. Our project advisor is Matt Nelson. He's the program coordinator for M2I. And we have our team mentor, Gary Stroick. Gary Stroick is very, very experienced in high-powered rocketry, has been doing it for years. He has his level 3 certification. He's affiliated with EEE, a EEE section in Minnesota. And our project mission is to design and construct a fully autonomous, high-powered rocket and ground support system that will be in charge of retrieving, launching and deploying a specimen autonomously. The specific requirements for the AGSE team are to autonomously retrieve and place a specimen into the rocket, orientate the rocket to 5 degrees off vertical away from the crowd, and then insert the igniter and commence the launch once the safety officer has given a go. The rocket team's specific requirements are to reach an apogee of exactly 3,000 feet using an air brake system. Now, air brake system is not a requirement. That's something that we chose to use to achieve this requirement. And then we're also required to eject the specimen at approximately 1,000 feet above ground level during the rocket's descent. We also are in charge of having a fully reusable rocket system so that it could be reprimed with a new motor, put back together upon descent, and fired off again.
So this is kind of a diagram of the current rocket design that we have right now. As you can see, starting from the aft end, or the right side, we have the motor mount, which will basically transfer the forces from the motor onto the actual airframe itself. Forward of that is the payload bay. The payload bay will contain the air brake system, which will be connected. The air brake system will consist of industrial strength, industrial grade servo, which will pull on some cables attached to the air brakes. We're still working on finalizing that design as throughout this month. Forward of that is the flight computer. The flight computer will consist of an inertial measurement unit, as well as a Hummingbird microcontroller, which we'll go into detail more. And that'll basically constantly predict the apogee of the rocket and give commands to the air brakes to control the apogee. Forward of that, the parachute bay 2. This will hold the drogue parachute of the rocket. This will deploy at apogee and will basically slow down the descent of the rocket to a stable descent, while still keeping the rocket from straying too far off from its landing zone. Forward of that is the avionics bay. The avionics bay will hold all of the altimeters, which will eject both parachutes from the parachute bay 1 and parachute bay 2. These altimeters use a barometric pressure sensor and the standard atmospheric table to record the altitude. When it detects apogee, the ejection charges fire, and the rocket separates, allowing the parachutes to deploy. Forward of that is the parachute bay 1, which will hold 2 more parachutes, which we'll go into more detail on that. Forward of that is the payload coupler, which is just, it will be an empty coupler, but it will also hold a GPS transmitter, which is a requirement. We'll go into detail more later. And then forward of that is the specimen bay, which will hold a specimen, the specimen that we're required to autonomously insert into the rocket and deploy at 1,000 feet AGL.
So here we have our schematic of our rocket as of right now. This is our model that we created in a program called Open Rocket. The rocket team mainly comprises this in making it. So right now we have a length of 126 inches, which is about 10.5 feet. Our diameter is 6 inches, and our mass is 438 ounces.
So as for our rocket design, we determined our length and spacing needed for the altimeter bay, the payload bay, and the specimen bay, and parachute bays and motor mount. Our couplers will be about 6 inches or 12 inches. We have some more specifications on the rocket. Our weight is determined as an estimate given airframe material selections and electronic package selections. The motor mount we selected through Open Rocket by doing a series of simulations. So we did those to test the apogee that we wanted to hit, which I'll talk about on the next page here. So we wanted to hit a height of 3,000 feet for the requirement from NASA, but we left some room at 3,412 feet. That'll give us room for changes in weights and how much height we need based on our air brakes and when they'll deploy. So that's that there. I'm going to have Connor talk about this here. These are our materials.
So for our materials for the body tubing, we chose to use a material called blue tube. It is similar to phenolic, except it's not baked or cured, which makes it a little bit more pliable, almost bendable, but not enough to affect like rocket building. It would just affect, it's better than phenolic because if phenolic is more brittle, if it's dropped, it can crack, which I know we've had problems with in the past. It's the best for the price. For our nose cone as well as our fins, we chose to use a fiberglass material. Fiberglass is the best for the price. For our nose cone, we have a type of fiberglass that is wound, which makes it just a lot stronger. And the fins are just easy to cut, easy to work with, and the best for the price.
This is kind of a design in the recovery scheme of our rocket. So you kind of see the diagram up on top, which I already talked about. And below you see two configurations, and these are the configurations during descent of the rocket. Configuration 1 will happen at apogee of the rocket. As you can see, the parachute bay 2 will separate from the avionics bay, which will allow the drogue chute to deploy. As said before, the drogue chute will just, the whole rocket will fall under the drogue chute to about 1,000 feet. A drogue chute will keep it stable descent whilst keeping the drifting of the rocket at a minimal level. Configuration 2 is where it gets a little more complicated. And configuration 2 is where we need to eject the specimen at 1,000 feet AGL to meet the NASA requirements. As you can see, what happens is the parachute bay 1 separates from the payload coupler. This is a complete separation and they become independent sections. While that happens, both the main parachute for the specimen bay and the main parachute for the other section deploy. So what you end up with 2 independent sections, and this qualifies, or this allows us to meet the requirement to eject this specimen. Now you can see a little deployment bag hanging down from the specimen bay. This deployment bag will contain the main parachute for the main independent section. When the specimen bay ejects when the specimen bay ejects from the parachute bay 1, a shock cord attached to that deployment bag will tug the main parachute out. So a combination of that tugging action based on, from the kinetic energy of the specimen bay as it is ejected out, as well as the ejection charge pressure behind the main, will ensure that that main parachute deploys and we don't have an entire rocket falling under just a drogue parachute.
The avionics bay contains the housing for our avionics equipment, and the goal of the project here is to deploy parachutes at proper time and sequence. For the drogue will initially be deployed, and then afterwards the main. There are 2 redundant altimeters provided by 2 separate companies, and this is used in that format to reduce any errors specific to each manufacturer. One official altimeter will be used for official scoring for NASA purposes, and Rebecca will continue this discussion on the recovery equipment.
So these are the altimeters that we've chosen for the recovery. And as you can see, they are all from separate companies. They all output about the same data and can be used to interpret the height and the descent of the rocket.
Specimen bay design. This is going back to the specimen bay at the very near the nose cone section of the rocket. Basically, we need to hold a specimen in the bay without, or properly contain the specimen during launch. So we can't have it vibrating, we can't have it shifting during launch, which would offset our CG and affect the stability of our rocket. We are currently looking into designs on that. Our original design was to use 3D printed foam, which we will use a 3D foam cutter for that, which will fit inside the specimen bay and allow a little room for the specimen to insert. We are still deciding on that design, so we don't have any diagrams on that yet. But some of the other requirements are easy integration with the AGSE system, which we will go into detail more. AGSE stands for Above Ground Support Equipment. This is a term that encompasses all of the autonomous specimen retrieval and insertion into the rocket. So obviously our specimen bay has to easily integrate with that system so that whatever arm we use to insert the specimen can easily enter the bay. Also our specimen door, the door to the specimen bay, which will need to be open to allow insertion of the specimen. We'll need to properly seal the specimen from outside environment. Basically, we can't have any of the airflow along the outside of the rocket body entering into the specimen bay. Not only will that be a concern to how we're sealing the specimen, it'll also be a concern that the rocket will be traveling at roughly Mach 0.45 at its max velocity, and any air entering in through the door could effectively rip out the door.
Yeah. And there's also been discussion of a system of redundant safety checks that we would be performing to ensure that the sample is actually fully inserted, as well as the door closed. We've had talks of using mechanical systems such as clicking or locking doors, or spring-loaded claws that will hold the sample within the bay. But we've also discussed using sensors that would communicate with electronics on board the rocket and the AGSE, so that the safety officer that is on scene with the rocket knows that the rocket is properly operating according to whether or not the specimen is fully inserted.
So one of our requirements is to reach a rocket apogee of exactly 3,000 feet, and we'll do this by using air brakes to control the rocket's apogee. And we'll have a flight computer that updates the rocket's predicted apogee, and it'll control the air brakes based on the difference between those two. And then we'll also have global positioning devices in that area.
The flight computer will have what we call an inertial measurement unit on board. This is a very accurate way to use an assortment of accelerometers, gyrometers, and inclinometers to measure the acceleration of the rocket accurately. What an inertial measurement unit does is it basically compares data it reads from accelerometers and gyrometers on board, and when they're out of sync or there's error between them, it updates the accelerometer. And that basically takes care of accelerometer drift, so you don't have drift error from the accelerometer. These units are very, very accurate and reliable. The particular one that we are looking into has a thermocouple on board to account for temperature effects to the accelerometer. So given the raw velocity and angular velocity, as well as a linear acceleration that we can retrieve from the inertial measurement unit, the flight computer will then update the rocket's predicted apogee, and based on that apogee, we'll determine whether or not to deploy the air brakes.
Yep, I will note that this is also a change from the proposal that we had initially submitted to M2I, purely in the sense that we discovered using a pedostatic tube and a thermocouple in conjunction to calculate the rocket's velocity we'd actually have issues with the instrument's accuracy and range available to it. Depending on the velocity that we anticipate the rocket flying at, we can bracket a certain number of, a certain range of velocities that it can measure, but it's not going to be accurate enough near apogee when the rocket is moving slower for us to properly calculate when we should extend the extend the air brakes to slow the rocket down. So we did actually make that change very, very recently.
So then we are also going to have GPS systems on board each part of the rocket that separates, and it will communicate with the receiver base station to allow the location of each portion to be monitored while it's descending. And then we'll have a microcontroller to facilitate the data transmission and store the data. And then this will be used exclusively for the recovery and location requirement.
Oh, that's not. Oh, yeah, it is. Okay. We're going to have a multi-function launch pad system in charge of autonomously finding and acquiring the payload sample, inserting it into the rocket, and launching the vehicle, all without user intervention. It will employ a microcontroller to process sensor input and issue output controls to servos. And the launch rail alignment will be done by a mechanical system consisting of pulleys, servos, and counterweights.
So in the corner of this slide here, we have a basic mock-up of our actual current AGSE design. So as you can see, we're using a crane system to that's actually going to locate and pick up the specimen and insert it into the rocket using visual sensors. To move the crane, we're using a two-pulley system. One pulley is going to actually move the up and down motion of the crane, while the other one will be using like the rover and the actual crane to move that left and right, I guess. There will be a servo on top of the crane in the same little box that I have an arrow driven, so that way the crane can turn with not having the whole base in the system turn. There will be another servo there at the base of the launch rail, at like the fulcrum, I guess, and that's actually going to pick up the whole launch rail and put it to the correct angle. We also, on the opposite side there, we'll be adding counterweights. This way we also put it at 5 degrees from horizontal. That way when the counterweight's at full, like straight up and downward, the whole rocket system will be sitting at 5 degrees, along with the support system on the crane to just add more support for the whole rocket system.
All right, along with the AGSE setup, we use aluminum components, which are easily disassembled for travel. They're lightweight, yet they're sturdy enough and strong enough to support the rocket rotating and launching according to NAR and NASA regulations. Specific manufacturers, mechanisms, and component configurations are being finalized. So we don't have the exact components, but we do know generally which components and which configuration we're going to go with.
All right, there's only so much to say about this here. This is our project timeline. We have a few big anticipated dates on here. Obviously, the competition will be April 12th through 17th. That'll be held in Huntsville, Alabama. We have a lot of wiggle room there with some of these hard dates that we put in for each of the sub-teams there on December 6th and January 21st. But essentially, for semester deliverables, we want to go to, which slide is it here? This one here. So these are the goals that we're actually looking to deliver this semester. We're supposed to organize and complete a final material list for all the materials being ordered. That includes weights and prices, and basically finalize all of our decisions before construction begins next semester. We want to complete a small-scale launch to fulfill the NASA student launch requirements and to provide experimental data for aerodynamic properties and altimeter testing. So basically, we just want to verify that our CD is even remotely accurate to what Open Rocket is actually giving us, and we're going to do that based on what our CD is predicted in Open Rocket versus what our altimeters actually show on our small-scale launch. And we also, which this is very important, we need to attain a level 2 certification by at least 2 of the team members according to NASA regulations. Our mentor is currently a level 3 cert, so technically we could still launch at the NASA competition, but I believe that they would look very well upon the fact that we have 2 or more members that are certified in level 2. because when we go to do our test launch, Gary will be there with us, but that way, we're at least kind of procuring the knowledge development in the high-powered rocketry region on our team. I'm going to go back here to our projected budget. Very, very detailed at a proposal level. We have everything estimated essentially that we're going to need. Some things have changed already and will continue to change, but this is a very rough draft of everything we're going to need. It's broken down into sub-teams. Our capital subtotal is about $8,400. That includes 10 students traveling, and with our group being 25 students, unfortunately that's less than half. So we'll be looking to other options in terms of getting more people to the competition with us if they choose to come. So just one more time, this is our project overview. We have short-term goals to finalize the AGSE design because it is one of the biggest factors of our entire project submission to NASA. We want to finalize the air brake subsystem design. This alone is going to accomplish the 3,000-foot apogee goal, and there is a huge point total that is weighted to hitting 3,000 feet exactly. For every foot off of that, we do lose points for the team as a whole. And number 3, we want to finalize the specimen containment design. This is equally as important as the previous 2. We just need to develop that system a little bit more and figure out exactly what sensors and safety checks we're going to use. And then the level 1 and 2 NAR certifications. That could also be through EEE, actually. Long-term goals. We want a subscale launch in December. We want a full-scale launch in February 2015. We want to have all of our systems tested out and essentially be ready to go by that point for the competition, and just use that as kind of a fail-safe in a way. Number 3, we're going to attend the student launch competition in April. Like I already mentioned, that's held in Huntsville, Alabama. For that one. And in closing, we are building a rocket for the launch at the NASA student launch competition. It's there's fully autonomous operations to retrieve, launch, and eject the specimen, constructing an air brake system to target a 3,000-foot apogee. And I suppose that's it, unless you have any questions for us. Oh yeah, I